In episode 20, titled 2.1 Query Optimization Basics, Indexing, Parameterization, Subsets, Temporary Tables, the focus is connecting faster queries to clearer thinking and smoother iteration, because performance is not just a technical concern. It affects how quickly an analyst can test ideas and confirm results. The CompTIA Data Plus DA0-002 exam does not expect deep database administration, but it does expect practical awareness of what makes queries slow and what habits reduce cost and delay. Slow queries create a feedback problem, where each adjustment takes too long, and that encourages guessing instead of careful validation. Good optimization habits also protect shared systems, because an inefficient query can consume resources and degrade performance for other users and workloads. The aim here is to build a set of repeatable basics that improve performance while keeping intent clear and results trustworthy. When these habits are stable, exam stems about timeouts, large tables, and slow reports become easier to answer. A strong first move is to limit columns and rows to essentials, because pulling less data reduces work across the entire query plan. Selecting only the needed columns reduces I/O and memory pressure, which can speed up both retrieval and downstream operations like joins and aggregates. Filtering early reduces the number of rows that must be processed, which matters because many expensive operations scale with row count. This is not only a performance trick, it is also a clarity practice, because choosing essentials forces the analyst to state what the question truly requires. Exam items often include distractors that select everything and filter later, which sounds flexible but is slower and more error-prone. A disciplined approach begins by naming the scope, limiting the dataset to that scope, and then performing calculations only on the scoped subset. That habit improves both speed and correctness because it reduces noise and reduces unintended side effects. Indexes are a core concept because they speed filtering and joining on keys by allowing the database to find matching rows without scanning the entire table. An index can be thought of as a lookup structure that maps values in a field to the locations of rows that contain those values, which makes common filters and joins dramatically faster. Indexes are especially useful for primary keys and frequently used foreign keys, and they can also help when filtering on dates or other high selectivity fields. The trade-off is that indexes require storage and maintenance because inserts and updates must also update index structures, which can slow write-heavy workloads if indexing is excessive. Exam stems often mention large tables, slow filters, or slow joins, and the correct reasoning often includes that indexing the join keys or filter keys improves performance. The key recall point is that indexes support lookup and matching, not broad full table operations, and they are most effective when queries can actually use them. Functions on indexed fields can block index use, which is a subtle but common reason a query becomes slower than expected. When a query applies a function to a field in a filter, such as converting a date, trimming a string, or changing case, the database may be unable to use the index efficiently because the indexed values no longer match the transformed values directly. The result is often a scan where many rows must be examined, which defeats the purpose of the index. A safer approach is to structure conditions so the indexed field can be compared directly to a constant or parameter, and to handle normalization in a way that preserves index-friendly comparison. Exam questions sometimes include this as a reasoning point, where two logically similar filters differ in performance because one preserves index usage and the other does not. The practical takeaway is that keeping predicates, meaning filter conditions, simple and index-aligned often matters more than adding clever expressions. Parameterization supports reuse and safety by allowing the same query logic to run against different inputs without rewriting the statement each time. A parameter is a placeholder for a value like a date range, a region, or a product category, allowing the query to remain stable while the input changes. This improves repeatability because the core logic is not constantly edited, reducing the risk of accidental changes that alter meaning. Parameterization also supports security and correctness in many contexts because it reduces the chance of unsafe input handling and encourages separation between logic and values. Exam stems that mention running the same report for different regions or time windows often imply that parameterization is appropriate because it makes the process consistent. The deeper concept is that stable logic plus variable inputs is easier to test, easier to audit, and easier to optimize. When the logic stays fixed, performance improvements carry forward across repeated runs. Subsets are valuable because they allow quick testing before full-scale runs, which reduces feedback time and helps detect logic errors early. A subset might be a small date range, a limited number of rows, or a filtered slice such as one region chosen to represent the structure of the full dataset without carrying the full cost. Subset testing helps validate joins, filters, and aggregates because mistakes are easier to spot when the output is small and can be inspected. It also protects shared systems because a full table scan on a production-sized dataset can create load that affects other users. Exam questions often include scenarios where a candidate must validate logic quickly or avoid timeouts, and using subsets is a practical answer that demonstrates disciplined iteration. The key is to choose subsets that preserve the characteristics that matter, such as key distributions and null patterns, rather than choosing subsets that make the data unrealistically clean. Temporary tables, often called temp tables, can break complex work into stages, which improves both readability and performance in many cases. A temp table stores an intermediate result, allowing the database to materialize a subset or a transformed view and then reuse it across later steps. This can reduce repeated computation, such as repeating the same filter and join logic multiple times, and it can make multi-step transformations easier to reason about and validate. Temp tables can also improve performance by allowing indexes on the intermediate result or by reducing the size of later joins and aggregations. The trade-off is that temp tables add complexity in management and can use additional storage in memory, so they should be used when they clearly simplify the workload. Exam stems that mention complex queries, repeated sub-expressions, or slow multi-stage reports often imply that staging intermediate results is helpful. The deeper idea is that staged work supports both performance and correctness because each stage can be checked. Expensive sorts and unnecessary distinct operations are common performance killers because they force the system to compare and reorder large amounts of data. Sorting is expensive when datasets are large because it often requires memory and disk operations, and it can become a bottleneck even when the final output is small. Distinct operations can be expensive because they require the system to identify unique values, often through sorting or hashing, and they can hide underlying data issues like duplicate keys that should be addressed directly. Exam questions sometimes describe slow queries that include ordering or distinct without clear need, and the intended reasoning is to avoid these operations unless they are required by the question. A disciplined query uses ordering only when the output must be ordered for consumption and uses distinct only when uniqueness is truly needed for correct meaning. When distinct is used as a bandage for join duplication, the query becomes slower and the underlying integrity issue remains unresolved.
Bottlenecks should be measured in simple terms by comparing time and row counts at different stages, because performance tuning is often about finding where the work explodes.
If a query runs slowly, one reason can be that a join multiplies rows unexpectedly, increasing the workload for later aggregation and sorting. Another reason can be that a filter is not selective, meaning it still returns most rows, which makes downstream operations expensive.
Comparing row counts before and after key operations helps reveal where the dataset grows, and comparing execution time across variations helps identify which change actually improved performance.
Exam stems sometimes frame performance issues as timeouts or long runtimes, and the correct approach often includes reducing data volume and identifying where the plan does too much work.
The key habit is to treat performance as a diagnostic process, not as a guessing game.
Keeping joins selective by filtering early is a high-yield tactic because joins are often where computation cost grows the fastest. If two large tables are joined and only then filtered, the join may process far more rows than necessary, creating overhead that could have been avoided by restricting each table first. Filtering early also clarifies intent because it ensures that only in-scope records participate in the join, reducing the risk of accidental inclusion of irrelevant records. This habit interacts with indexing because filtered join keys often benefit from index lookups, while unfiltered joins may require scans and large intermediate results. Exam scenarios that mention slow reports often include opportunities to filter earlier, such as limiting to a time window or a set of categories before joining to descriptive tables. The professional reasoning is that selectivity should happen as soon as the question allows because early reduction improves both speed and interpretability. Readability should be balanced with performance because clever but fragile tricks can make a query hard to maintain and easy to misinterpret. A query that is fast but confusing can produce trust problems because reviewers cannot verify intent and small changes can break logic in surprising ways. Clear naming, consistent formatting, and staged logic can often produce both good performance and good clarity, especially when combined with early filtering and selective joins. When performance tuning requires changes that reduce readability, the reasoning should be documented so future reviewers know why the structure exists. Exam items sometimes reward the choice that is both reasonable in performance and clear in intent, rather than the option that introduces complicated patterns without necessity. The main point is that sustainable optimization is usually simple, not magical, and it keeps the query aligned with the question being answered. Timeouts are often prevented by controlling result size and using pagination when appropriate, because large result sets can overwhelm systems and users even when the underlying query is correct. Limiting results for exploratory work keeps feedback fast and prevents pulling unnecessary rows across networks. Pagination supports consumption of large datasets in manageable chunks, especially when the goal is to review or export rather than to compute a single aggregate. Many systems also have limits on response size and execution time, so controlling output size is both a technical necessity and a good habit. Exam stems that mention timeouts, slow dashboards, or failed exports often expect recognition that results should be constrained and that summary outputs are often better than raw dumps. The key idea is that not every question needs all rows, and pulling all rows is often a sign that the question has not been translated into a precise query goal. A simple tuning sequence is valuable because it creates a repeatable approach that can be applied under exam pressure without needing deep system knowledge. The sequence begins by restating the question and cutting the selection down to required columns and required rows because volume is the first driver of cost. Next, it applies filters early, and checks whether indexes can support the key filters and joins, because selective access often yields the largest gains. Then, it checks joins for row multiplication and removes unnecessary sorts and distinct operations that add heavy overhead. After that, it uses subsets and temp staging when multi-step logic is needed, validating each stage with row counts and small sample checks. Finally, it controls output size to prevent timeouts and keeps the query readable so intent remains verifiable. This sequence is simple enough to remember and aligns with the exam's preference for disciplined, defensible reasoning.
To conclude, query optimization basics are about reducing unnecessary work while keeping intent clear, because fast iteration supports better analysis and better validation.
Limiting columns and rows early, keeping joins selective, and using indexes on common filter and join keys are foundational habits that often produce the biggest gains. Avoiding functions that block index use, reducing sorts and distinct operations, and measuring bottlenecks with time and row counts prevent guesswork and reveal where the plan is doing too much work.
Parameterization supports safe reuse, subsets support quick testing, and temporary tables support staged reasoning for complex queries.
Controlling result size prevents timeouts and reduces strain on systems and users, while balancing readability keeps the work trustworthy and maintainable.
One optimization habit to adopt this week is to treat early scope reduction as mandatory by always naming the time window and selecting only needed columns first, because that single step improves performance and clarity in almost every scenario.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.